Hello boys, this is practice test 2, which is a revised version. I'm giving you work solutions this time. Okay, so let's have a look at question 1a. 1a is asking us to find the derivative of the square root of 4x squared minus x. Okay, first thing to do is to rewrite this one in what I call calculus friendly form. That is, using indices where possible. So we know the square root of anything is that thing raised to the power of a half, and that's all I've done here. No calculus involved, just writing it in index form. Now for the calculus, we use the chain rule, or the function of the function rule. As you know, you grab the index, put it out front. There we go, that's explaining that half. I rewrite what's in brackets, don't touch it, reduce the index by 1, and then times by the derivative of what's in brackets. Derivative of what's in brackets is quite clearly 2 times 4 is 8x minus 1. There you go. Now the rest is tidying up. That's the calculus done. Be careful of these fractions a bit. That 2 goes underneath, so we can really isolate this half. That's what I like to do. Take it out the front, and then we realise that this is upstairs. It's times 8x to the minus 1. So that goes upstairs, and underneath we get the square root of 4x squared minus x. Now why that is the case is that minus a half is saying you can put it downstairs by changing the sign of the index, so from negative to positive, and we know that anything raised to the power of a half is a square root of that thing. Tidying this up just a touch, we can get rid of this 1 here and just call it, as I've called it there, 8x minus 1, that says, over 2 square root 4x squared minus 1. Question 1b is a fairly stock standard question when we're finding the tangent to a curve. We follow the same procedure in all these situations. Firstly, what we really want to find is an equation of the form y equals mx plus c, the standard form for a linear equation. Now the first job is to find m, and we find m by differentiating y. Remember, the derivative of y is sometimes called the derivative function, or gradient function, sorry, the gradient function. And so we find m by differentiating this and letting x equal 0. Why do we want x to equal 0? Well, x is going to equal 0 at the y-intercept, and that's where we're finding the tangent at. Having found m, we substitute it into the standard form y equals mx plus c, and then we're going to find c by substituting 0, 1, y 0, 1, because that's where the y-intercept is for this equation. You let x equal 0 to find the y-intercept, don't you? So when x is 0, y will equal 1 over 1 cubed, which is just 1. So we substitute 0, 1 into that equation to find the value of c, and that's what I've done here. So firstly, we've got to put our equation into calculus friendly form, so we can do that by just taking this all upstairs and reversing the sign of the index. The differentiation is achieved by using the function of a function rule, or the chain rule, and we take that negative 3, put it out front, reduce the index by 1, leave what's in brackets as it is, and times by the derivative of what's in brackets, which happens to be 1. So when x is 0, y dash is equal to negative 3. So we're letting x equals 0 there. We've got negative 3 times 1. 1 to the power of anything is still 1. So this is all going to come to negative 3. Okay, so y equals negative 3x plus c. That's what we've found out so far. And to find the value of c, we let a point on the line, we substitute that point in the line into our equation. So we're interested in where x is 0 and y is 1, because that's where the y-intercept is, remember. So when y is 1 and x is 0, c is going to equal 1. So we've got everything we need. We just now need to substitute the values of m and c back into our original template, and we find y equals negative 3x plus 1. Okay, for this one, we're maximising the area of a rectangle. Often that will result in a square shape, and it does in this case. So what's the maximum rectangular area that can be fenced off if 128 metres of fencing is available? It's never a bad idea to visualise these things by drawing a quick diagram. We have this is a very dodgy looking rectangle here, admittedly, but I'm letting the length equal x and the width equal y. And we know that the area of a rectangle is just width times length, but in this case it's x times y. We also know one other thing about this rectangle, and that's its perimeter is going to equal 2 lots of x, so the perimeter is just the distance around the object, so it's 1 lot of x there plus that, plus 2 lots of y by similar reasoning, y plus y is 2y, and but the perimeter does equal 128 metres. So we can say that 128 metres, or 128, equals 2x plus 2y. And we can divide through by 2 just to make things a little easier. So I've just divided that by 2, that by 2, and that by 2 to come up with x plus y equals 64. Now, y equals 64 minus x. So what I've done is I've subtracted x from both sides. Why did I do that? Because I know the area is x times y. But I can't find the derivative of that unless I get rid of one of the variables. And I can get rid of one of the variables by noting that y is just equal to 64 minus x. So I can replace that y with that 64 minus x. And here we go. So area equals x times 64 minus x. And expanding that out, we get the area equals 64x minus x squared. Okay, now what we need to do is find the derivative of that and let the derivative equal 0. So dA dx is equal to 64 minus 2x, isn't it? Minus 2x. And so if we let that equal 0, we discover that 64 minus 2x equals 0. 2x equals 64. I'm just adding 2x to both sides and reversing the order. Therefore, x equals 32. Now if x equals 32, and we noted above that x plus y equals 64, there it is right up the top of the screen, y must equal 32 as well. Therefore the maximum area, remember the area of our rectangle is just x times y, is 32 times 32, which equals 1024 metres squared. Question 2a, some fairly basic integrations. These are indefinite integrals, and we call them that because they don't have a definite numeric answer, and you know that they're indefinite integrals because there are no limits upper and lower. And so what we're ending up with is an algebraic expression as our answer, and that answer will always have a plus c, a plus a constant, and I've been through many times why that is so. Okay, first one. Now there's absolutely no tricks to this one. What we do is we raise the index by 1 and divide by the new index, term by term. So x squared goes to x cubed on 3 minus, there's an invisible 1 there, a little bit visible now, x to the power of 1. Raise that by 1 to get x squared and divide by the new index, 2. And that's how we get that one. Plus 10x. Now to any number, to any constant that you're integrating, you simply add an x. That you can think of it this way. That's really equal to 10 times x to the power of 0. So we increase the 0 by 1. So we get x to the power of 1 and divide by 1. So in any event, it just comes to 10x, and there's our plus c. Here, we make use of the sort of chain rule of integration, and it only works when we've got what's called a linear factor in the brackets. In other words, when it's something or rather x plus or minus something, or rather in terms of a number. Okay, it only works then. It won't work if we've got an x cubed or an x squared or a square root of x, anything like that in our brackets. Okay, so apart from that, it's fairly similar to the general rule. All we need to do is write down what's in brackets, increase the index by 1, divide by the new index. That's the same as what we did over here. But this time we've just got to multiply the denominator by the derivative of what's in brackets, and that's 3. So this one's going to equal, well, what I've written down there, except we wouldn't leave it as 8 times 3, we would change it in the next line to 24, and that one is done. At least it is now. Let's quickly look at some definite integrals. Okay, so These are not necessarily area problems, they might be, but in this case we don't say that it is, so we don't treat it as one. Here all we do is we integrate as usual, so we've got a constant number. 0.5 is just a number, so we integrate that in the usual way to get 0.5x, put our limits in there, and remember what the go is, we substitute the upper limit, that's what we've done there, 0.5, and x is 5 times 5, and we always subtract the lower limit, which happily in this case is 0. And 0 times anything is 0. So our answer here comes to 5.2. Our next example contains one little trick, and what we need to do first is to expand out the brackets here so that we can integrate. And so this is t to the power of 1, isn't it? Times t to the power of a half. So that's t to the power of 3 on 2, 1.5. Minus t times 1 is t. So minus t dt, we're integrating in respect of t is what that means. Now, okay, so the integration proceeds. In the usual way, we add 1 to the index. So 3 on 2 becomes 5 on 2, and we divide by the new index, 5 on 2. Minus, and we know how to integrate that, it's just going to be t squared on 2. Now when we here what we do, when we divide by 5 on 2, that's the same as multiplying by 2 on 5. Just note what I've done there, and I haven't touched this area here. Now we substitute our limits in, and again we've got a lovely 0 there that's not going to make it a bit easier. So all we've really got to worry about is substituting the 3 in, because when I substitute the 0 in, that comes to 0, so does that. So there we go, instead of the t we've now got a 3. That's all we've done there and there, and when you evaluate that very carefully on your calculator, it'll come to 1.74 to 2 decimal places. In the question I didn't say how precise you have to be, but when you indicate your answer, you tell me how precise you'll be. The next part of the test, question 3, is in a separate video, so watch out for that.